Okay, so let's unpack this. You've probably seen it before, right? ma equal F. It's like one of those famous equations from high school physics. But what does it really mean? I mean, beyond just a formula you plug numbers into, it turns out it's actually a definition, a way of understanding the fundamental nature of force itself.
Yeah, what's really fascinating here is that force is a word we throw around all the time, We talk about strong forces, weak forces, we even force ourselves to get out of bed sometimes. But actually pinning down a clear scientific definition, that was a huge leap. So today, drawing inspiration from King Tuako's book, The Amazing World of the Equation of Motion, we're going to do a deep dive into this equation. We want to demystify what force really is, look at Newton's big ideas, his laws, and find some surprising ways they show up. Everywhere from tablecloth tricks to launching rockets.
Right. And our mission here is simple. Give you that shortcut to being really well informed. We want to pack this with surprising facts, maybe some aha moments. We'll start with defining force, trickier than it sounds. Then we'll look at how it works when things are still and when they're moving. Then we'll get into Newton's whole framework. And finally, check out inertia in action. So, ready to understand the sort of invisible magic governing everything around us, let's jump right in. We all kind of feel force, don't we? Pushing, pulling, lifting, it's intuitive. But going from that feeling to a precise scientific definition, that was the big challenge. How did Newton actually do that with man F, and why was it such a game changer?
That really is the heart of it. Before Newton, people like Aristotle thought objects needed a constant push or pull just to keep moving. Stop pushing your cart, and, well, it stops, right? Seems logical. But Newton's second law, F equals ma, it just shattered that idea. He said force isn't needed to maintain motion. Force is what changes motion. So force itself is defined as the thing that causes acceleration. Imagine like a super smooth ice rink, perfect ice. You give a little puck a push, it doesn't just stop when your hand leaves it, does it? It glides. Your push, that was the force. And the change from 0 speed to moving, that was the acceleration.
Ah, okay. So force is about the change, not just the motion itself. That's a really key difference.
Okay.
But then you got the M's in there. Mass. Why does mass matter in this definition?
Mass is, well, it's crucial. It represents the object's own resistance to that change in motion you're trying to cause. Think of it as like built-in reluctance. It's stubbornness. You push that little hockey puck, it accelerates easily, right? Now try pushing, say, a heavy bowling ball with that exact same push. It's going to accelerate much less, maybe barely at all. If you rearrange the equation, you get a Fm. That makes it super clear. For the same force F, if the mass m is bigger, the acceleration a has to be smaller. So mass, in this whole picture, is basically a measure of inertia. It's resistance to being nudged from whatever it's currently doing.
Right, inertia. We'll definitely come back to that. But this brings up another point. Measuring force. We talk about strong pushes, weak pulls. That's all subjective, isn't it? How did FMOM give scientists a way to actually, put a number on force, make it precise?
Yeah, that's a great question. How do you get from just a feeling that felt strong to a number everyone agrees on? Physics cleverly uses the equation itself to define the unit. 1 Newton we rated as N is defined as the force you need to make a 1 kilogram object accelerate at 1 meter per second. It directly links the cause, the force, to the effect, the acceleration of a specific mass. No ambiguity.
And to give you a real feel for that, it's not just abstract. Think about holding a D-cell battery, like one of those big chunky ones that weighs about 100 grams. The downward force you feel from gravity holding it, that's roughly 1 Newton. Or a 1 kilogram carton of milk, holding that feels like about 10 newtons. But then you scale it up. A pro boxer's punch, that can be over 5,000 newtons, easily. And the thrust from a big rocket like a SpaceX Falcon 9 taking off, we're talking over 7.6 million newtons. So this 1 unit, the newton, suddenly gives us this incredible range to compare forces, from tiny to absolutely immense. Okay, so S means force causes acceleration. Got it. But what about when things aren't accelerating? Like my coffee mug is sitting here on the desk, it's not moving. Does that mean zero force is acting on it, or is something else going on?
Fantastic question. And that brings us to the idea of net force, or, the total force. That mug on your desk, it looks completely still, right? But it's actually in what we call equilibrium. Gravity's pulling it down constantly with a certain force. But the desk is pushing back up on the mug with a force that's exactly equal, but in the opposite direction. We call that upper push, the normal force. So you've got the downward pull of gravity, the upper push of the desk. They perfectly balance, cancel each other out. The net force, the total sum, is 0. And if F is 0 in FMA, then A, the acceleration, must also be 0, so it stays put.
Ah, okay. So stillness doesn't mean no forces. It means balanced forces, a kind of silent tug of war. What if, say, an apple was floating in water, also perfectly still? Is it the same idea, just different forces balancing?
Exactly the same principle. Gravity is still pulling the apple down, of course. But this time, the upward balancing force isn't a table, it's buoyancy. It's the upward push from the water itself. Comes from pressure differences in the water, actually. Archimedes figured that out. So, yeah, whether it's on a solid table or floating in a liquid, if an object is static, not accelerating, the net force on it has to be zero. All the pushes and pulls are in perfect balance.
That makes sense for things that are sitting still. But what about things that are moving but not speeding up or slowing down? Like, imagine a curling stone just gliding smoothly across really good ice, constant speed.
Another great example. And yes, it's still about zero net force. If an object is moving at a constant velocity, and that means constant speed and constant direction, then its acceleration is zero. It's not changing its motion. And again, if A is zero, then ESMA tells us the net force F must also be zero. The curling stone just keeps doing what it was doing because there's no unbalanced force acting to change things. And this tendency, this property of objects to just keep doing whatever they're doing, whether that's staying put or moving steadily, unless some outside force messes with them. That's what we call inertia. It's almost like the universe is inherently a bit lazy. It prefers things to just keep going as they are.
Huh. Cosmic laziness. I like that. And it's surprisingly powerful, this inertia. But okay, what happens when that lazy curling stone slides off the perfect ice onto, say, a rough carpet? It slows down pretty quickly and stops. What's going on there? What's interrupting its glide?
Right. So now the acceleration isn't zero anymore, is it? It's actually negative acceleration because the stone is slowing down, decelerating. And that immediately tells us, from EFNA, that there must be a net force acting on it now, an unbalanced force. And the culprit here, it's friction. The carpet exerts a frictional force that pushes against the stone's motion. It opposes the direction it's trying to slide. This friction is an unbalanced force, and it's what steals the stone's motion, brings it to a stop. If you could get rid of all friction and air resistance too, like a comet out in deep space, then yeah, that curling stone, once you pushed it, would literally just keep going forever. Same speed, same direction. It really shows how much friction shapes our everyday experience, often without us even noticing it.
It really is incredible when you think that these ideas, which seem so fundamental now, weren't always obvious. Newton didn't just, stumble upon an equation. He pieced together this whole new way of seeing how motion works, built on what came before, but synthesize it. He gave us this grand unified theory for everyday motion.
Absolutely. For centuries, Aristotle's view held sway: you need force for motion, period. It was really Galileo Galilei who started seriously questioning that, suggesting that maybe without resistance, things would just keep moving. Newton took Galileo's insights and others and formalized them into his 3 laws. They're so elegant and powerful. First, the law of inertia. Basically, Galileo's idea refined: things stay put or keep moving steadily unless you push or pull on them with an unbalanced force. It's the default state. Second, the law of motion. That's our EFMA. It quantifies it. It tells you exactly how much the motion changes based on the force and the mass. It's the engine of change. And third, the law of action-reaction. For every action, there's an equal and opposite reaction. Forces never happen alone. They always come in pairs.
Okay, that third one, action-reaction. So when a big rocket blasts off, pushing all that hot gas downwards, that's not just pushing gas, it's the gas pushing the rocket upwards with the same force. Is that it?
Precisely. The rocket pushes down hard on the exhaust gases. That's the action. The reaction is the exhaust gases pushing back up on the rocket, equally hard. And that's the force that lifts it. It's everywhere. When a swimmer pushes off the wall or even just pushes water backwards with their hands, the water pushes them forward. When you walk, your foot pushes backward on the pavement.
And the pavement pushes you forward.
Exactly. It's this beautiful symmetry. You can't have a push without a pushback. Forces are always an interaction, a two-way street. No isolated forces exist.
Wow. And what gets me is how these laws, especially inertia, show up in really unexpected ways, almost like magic tricks that aren't magic at all.
Oh, absolutely. Think about a carpenter trying to get a blade out of a wooden hand plane. They don't hit the heavy metal blade itself, do they? They tap the wooden base sharply downwards. What happens? The light wooden base accelerates downwards quickly because of the tap. But the heavy metal blade, because it has much more mass, has more inertia, it resists that sudden downward motion. So the base effectively gets knocked out from under the blade, loosening it. It's cleverly using inertia.
Or the classic tablecloth trick, where someone yanks a tablecloth out from under a full setting of dishes, glasses, and everything just stays put.
Yeah.
It seems impossible.
Pure inertia in action. It looks amazing, but it works because of two things: the mass of the dishes and the speed of the pull. You have to pull the cloth really fast, a quick, sharp yank. This minimizes the time that the friction between the cloth and the glasses can actually act. Because the time is so short, the force transferred is tiny, not enough to overcome the inertia of the glasses. Their mass makes them want to stay right where they are. So they do. It's the exact same physics behind that Japanese stacking game, the Rumulatoshi. You knock out the bottom blocks, and the top ones hang there for a split second because of inertia. So, today we've really seen how this one equation, May ATF, and Newton's three laws tied together, they don't just describe forces, they fundamentally define what force is in the physical world. From feeling the slight weight of a battery in your hand to understanding the colossal thrust of a rocket. These principles give us the power to predict, to control, even to engineer motion. It really was a profound shift in how humans understood the universe, moving away from just gut feelings to a precise mathematical language for mechanics.
It's been a fantastic deep dive. It shows these ideas aren't just, dry formulas you memorize for a text. They're genuinely powerful tools. Tools for understanding why your mug stays on the desk, how a comet cruises through space, even the little forces involved in just walking across the room. Hopefully this gives you a completely fresh way of seeing all the forces constantly at work around you every single day, things you maybe never really noticed before. So thinking about all this, what does it mean for you? Here's our provocative thought to leave you with. Now that you've got a clearer picture of force, inertia, and action-reaction, what are some of those invisible forces you start noticing in your own daily life? Maybe it's how your body pushes back into the car seat when you accelerate, or why you lean into a turn, or even just the feeling of pushing off the ground with each step. What forces, what moments of inertia or reaction do you see now that maybe you were blind to before?